If a storm type most Americans have never heard of just produced the single most expensive thunderstorm event in recorded U.S. history, and the emergency manager on the ground said he didn't even know such a storm was possible, and the science published in the last 2 years says that storm's geographic footprint has expanded nearly 5 times in 4 decades, then Signal Watch needs to be talking about this. Hit like and subscribe to Signal Watch so you don't miss a single update as this investigation develops. Drop a comment with where you're watching from, what time it is there, and tell me, have you ever been through a derecho? Did you even know what it was when it hit? If you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You are the reason we can keep chasing stories like this, so thank you for having our back. Now, 4 things you need to know before we get into it. A storm that traveled 770 miles through 8 states in 14 hours, and the Storm Prediction Center's own risk outlook called it marginal the morning it happened. Buildings in downtown Houston designed to withstand 150 miles per hour winds shattered by a storm that never reached half that speed, and the physics of why engineers got it exactly wrong. The most dangerous part of a derecho isn't the wind, it's what happens to the grid in the days and weeks after, when the heat arrives and the lights stay off. And a study published in Nature Climate Change showing the geographic area hit by these storms has expanded nearly 5 times in 40 years. Now, settle in and let's get into it. On the morning of August 10th, 2020, the Storm Prediction Center issued its Day 1 convective outlook for the central United States. Iowa and northern Illinois were shaded in the lightest possible color, marginal risk. 1 out of 5, the category reserved for days when severe weather is possible but not particularly likely, when most people decide the day looks fine and go about their lives. It did not look like a day that would rewrite the record books. By 2:30 that afternoon, Cedar Rapids, Iowa was experiencing winds the National Weather Service would later estimate at 140 miles per hour, equivalent to a Category 3 or 4 hurricane. Winds that don't belong in the middle of a continent, produced by a storm that wasn't supposed to be there. That morning's outlook wasn't negligence. It wasn't incompetence. It was the honest output of some of the best forecasting systems in the world applied to a type of storm that consistently, structurally, and physically outpaces the tools designed to predict it. The National Weather Service office in Omaha issued its first warning at 8:45 a.m. The first damage reports came in from Omaha 8 minutes later. Not 8 minutes after the storm hit. 8 minutes after the warning, the gap between the alert and the impact was the length of a coffee break. By the time most Iowans had looked at their phones, the storm was already on top of them. What followed over the next 14 hours was the kind of event that meteorologists describe carefully and precisely because the numbers are so large they risk sounding exaggerated. The system traveled 770 miles, crossing 8 states: South Dakota, Nebraska, Iowa, Wisconsin, Illinois, Indiana, Michigan, and Ohio. It left a damage corridor 50 to 100 miles wide. In Omaha, the largest city in Nebraska, over 50,000 people lost power within minutes. 1 week after the storm, nearly 7,000 Omaha residents were still waiting for restoration. But Omaha was not where it was worst. The highest measured wind gust, 130 miles per hour, was recorded 2 miles northeast of Clinton, in Clinton County, Iowa. When NWS surveyors arrived in the days after and assessed the physical damage, they estimated the winds in some locations may have reached 140 miles per hour. That number, 140 miles per hour, is not a gust in any ordinary sense. It is the sustained wind speed of a major hurricane, concentrated in a straight line over hundreds of miles of the American heartland in the middle of the afternoon. Cedar Rapids, a city of roughly 275,000 people, lost 98% of its electrical power simultaneously, not cascading outages over hours, 98%, at essentially the same moment. That number is the beginning of the primary question this investigation will answer. Not just what happened, but why a storm this powerful so consistently arrives ahead of its warning, and what it means for the infrastructure in its path when it does. Because the forecasting gap is only one part of what makes August 10th, 2020, the defining case study in this story. While meteorologists scrambled to upgrade their outlooks that morning, watching the SPC's risk category jump from marginal to slight to enhanced as the storm intensified in real time. The storm itself was doing something that no single weather event is supposed to be capable of. It was destroying the power infrastructure of an entire multi-state region simultaneously. And the scale of what it left behind is something that emergency managers later admitted, on the record, they had no framework to handle. The word derecho comes from Spanish. It means straight or direct, doctor. Gustavus Hinrichs, a physics professor at the University of Iowa, coined the term in 1888 to distinguish the straight-line winds produced by certain severe thunderstorm complexes from the rotating winds of tornadoes. The terminology sat mostly in the meteorological literature for nearly a century, before it re-entered scientific usage in the 1980s. Most Americans still haven't heard it. That ignorance is itself a data point. Because this storm type is not rare, it is not exotic. According to the Storm Prediction Center's climatological maps, compiled by researcher Dennis Kane, much of the central and eastern United States averages one moderate to high intensity derecho every 2 years. The corridor stretching from the lower Mississippi Valley through the Ohio Valley and the southern Great Lakes, the area that includes Chicago, Indianapolis, Columbus, Cincinnati, Louisville, St. Louis, Memphis, Kansas City, averages one per year. The SPC calls this corridor Derecho Alley. It runs directly through the most densely populated inland region of the country. So let's be precise about what this storm type actually is, because the precision matters. As of May 10, 2025, NOAA and Environment and Climate Change Canada formally revised the official definition of a derecho. The new criteria, applied algorithmically to eliminate ambiguity, require a wind damage swath extending more than 400 miles, wind gusts of at least 58 miles per hour along most of its length, at least 3 wind reports of at least 75 miles per hour separated by 80 miles from each other, and an origin from a mesoscale convective system moving faster than the mean wind speed. This was the second definition revision in roughly 3 years. The previous revision, in January 2022, had already expanded the required damage swath from 240 miles to 400 miles. When the regulatory body keeps revising the definition, something real is prompting the revision. A derecho is not a tornado. A tornado is typically hundreds of yards wide. Even the widest tornado on record in the United States was 2.6 miles across. A derecho damage corridor is 50 to 100 miles wide and hundreds of miles long. It is not a hurricane. Hurricanes form over warm ocean water and decay rapidly over land. A derecho forms over land and feeds on it, on the moisture pooled ahead of summer fronts, on the thermal instability of heat waves, on the very atmospheric conditions that make mid-continent summers dangerous in the first place. The derecho's fundamental structure is the bow echo, a radar signature shaped like a backward letter C, the product of a mesoscale convective system that has organized itself into a self-sustaining, self-accelerating engine. The bow itself is a visualization of physics. The middle of the convective line races ahead of its flanks, driven by the outflow boundary of its own cold pool. That middle section, the apex of the bow, is where the winds are fastest and the damage is worst. It typically moves at 40 to 60 miles per hour. On exceptional days, faster. According to research published in the journal Earth and Environmental Systems Modeling, derechos account for approximately 20% of all damaging wind gust reports across the central and eastern United States, despite being far less well known than tornadoes. 20% of the wind damage record, from a storm most Americans have never heard of. The definition keeps changing because our understanding of what these systems can do keeps being revised by what these systems actually do. That revision is where this investigation begins. The full accounting of what August 10th, 2020 did to Iowa takes time to absorb. Not because any single number is especially complicated, but because there are so many of them, and they stack in a way that becomes hard to process. Start with the power. Between August 10th and 13th, 2020, 1.9 million customers were affected by power outages across the multi-state derecho path. The maximum simultaneous outages reached 1.4 million customers, 759,000 in Illinois, 585,000 in Iowa, 283,000 in Indiana, and 345,000 across Missouri, Wisconsin, Michigan, and other affected states. In Iowa alone, 480,000 outages were reported after the storm passed. 3 days after the event, over 100,000 customers in Illinois and 200,000 in Iowa remained without power. A week after the storm, 75,000 Iowans, most of them in Lynn County, still lacked electricity. 40,000 Cedar Rapids residents were without power, at least through August 17th. Mediacom, the telecommunications provider serving the affected region, reported 340,000 customers lost internet access across the impacted states. On August 12th, 2 days after the storm, Mediacom reported 57,000 modems offline in eastern Iowa alone, most of them in the Cedar Rapids area. 2 days after that, nearly 10,000 of those customers were still without service. Radio masts and towers were damaged or destroyed across the damaged corridor, causing radio outages and disrupting mobile phone service at precisely the moment people most needed to communicate. The 14 days following the storm were characterized in the Iowa Department of Homeland Security and Emergency Management's own post-event review as a period when communication capabilities throughout the state varied, and in some areas there was consistent conflict of information. Semi-trucks full of ice arrived in communities unprompted. Department of Transportation workers reached dump sites only to find they'd been given inaccurate operating hours. The communication infrastructure that emergency management depends on had failed at the same moment as the power infrastructure it runs on. The IDHSEM review's most arresting finding was this. Many interviewees stated that they were unaware of the severity of the incoming storm, leaving citizens across multiple counties unaware of the hurricane-force sustained winds and the increasing storm impacts to communities in its path. Lynn County Emergency Management Director Steve O'Connick, speaking to Iowa Public Radio in the days after the storm, described his experience in words that should be in every infrastructure planning document in the country. I didn't know there was such a thing. He was not alone. According to multiple post-event reports, thus many Iowans had never heard the word derecho before August 10, 2020. Beyond the grid, the agricultural accounting was staggering. Arlen Suderman, chief commodities economist for the firm StoneX, estimated the damage to Iowa crops at 200 to 400 million bushels of corn and soybeans. Roughly 850,000 acres of Iowa farmland was damaged. The Iowa Department of Natural Resources reported the derecho damaged trees on more than 56,800 acres of forest land statewide, and later analysis estimated that 2.67 million trees were damaged or killed on Iowa forest land alone. 8,000 homes across the affected region were severely damaged or destroyed. The total cost, $11 billion. The National Weather Service's formal designation, the most expensive thunderstorm event in modern United States history. That record stood because of the storm's scale, not its intensity alone, but the simultaneous application of that intensity across hundreds of miles of inhabited land and the infrastructure threading through it. It wasn't the worst wind at any given point. It was the same catastrophic wind at every point, all at once. There is a name for that kind of event in other contexts. We call it a catastrophic system failure. August 10th, 2020 was that, for the power grid, for the communications network, for the agricultural sector, and for the emergency management frameworks that were designed for a different kind of storm. Houston calls itself the energy capital of the world. It is home to more than 600 energy companies and the headquarters of more major oil and gas firms than any other city on the planet. It is also home to CenterPoint Energy, one of the country's largest electric distribution utilities, which serves 2.6 million metered customers across the greater Houston metropolitan area. On the afternoon of May 16, 2024, a derecho swept across southeast Texas from west to east and produced wind speeds the National Weather Service estimated at 100 miles per hour. By the time the storm had passed, 1 million of those CenterPoint customers, in the energy capital of the world, had no power. 8 people died in Harris County as a direct result of the storm and its aftermath. 2 tornadoes spawned by the derecho complex added to the destruction. The damage to downtown Houston's skyscraper corridor was so extensive that it would become the subject of engineering research papers published months later. But the scale of the infrastructure damage is what defines this event as a case study. CenterPoint, Energy's post-storm emergency response, required mobilizing more than 7,700 frontline electrical workers, contractors, and mutual aid resources from 8 states. The company deployed 700 damage assessors to survey more than 490 distribution circuits containing 7,147 overhead circuits. What they found required replacing more than 400 miles of primary electrical wires, more than 1,600 transformers, approximately 1,600 power poles. 5 days after the storm, on May 21, 2024, more than 130,000 homes, businesses, and schools in the Houston area remained without electricity. CenterPoint issued a statement that day saying restorations should be substantially complete by Wednesday. That was day 6. Harris County Executive Judge Lena Hidalgo, briefing residents shortly after the storm, delivered a warning that most people didn't want to hear. Some customers tied to the 10 transmission lines that had been completely downed could be waiting a couple of weeks for power restoration, just like in Hurricane Ike. And the heat was coming back. Space City weather meteorologist Eric Berger, speaking on Houston Matters Radio on May 21st, was direct. The power needs to be restored by this weekend. There will be no relief during the daytime, and even the nights are going to be really warm. For the city's most vulnerable residents, the combination of no power and rising temperatures became life-threatening. Houston Mayor John Whitmire announced publicly that hundreds of seniors in an assisted living center had been discovered in the days after the storm, without food, water, or air conditioning. His response was unambiguous. "I've even thought about, is this criminal neglect involved?" The carbon monoxide deaths began. A man who ran a portable generator indoors became the 8th Harris County fatality tied to the derecho event. CenterPoint's outage tracking map crashed during the event, unable to handle the volume of simultaneous outage reports. In the absence of functioning tracking tools, residents could not determine when their power would be restored. Families with young children drove in circles, seeking air-conditioned spaces. Elderly people sat in cars. A 2-month-old baby's family reported spending days driving from place to place to find functioning air conditioning. CenterPoint's eventual cost filing with the Public Utility Commission of Texas sought approximately $450 million in emergency response costs. And that number covered only the May derecho. It did not include the cost of Hurricane Beryl, which struck Houston 2 months later in July. The company proposed spreading the recovery costs over up to 15 years through securitization. 1 million customers without power, 8 deaths, $450 million in infrastructure replacement costs, in a single afternoon, in the energy capital of the world. But the Houston derecho didn't just knock out the lights. It destroyed things that were, by every engineering standard in existence, not supposed to be destroyable. And that story, the story of the buildings, is where the physics of this threat becomes genuinely alarming. Before Iowa 2020 and Houston 2024, there was June 29th, 2012. And in some ways, the 2012 derecho is the most important case study in this investigation, not because of its size, though it was massive, but because of the institutional record it left behind. The storm started as scattered thunderstorms over eastern Iowa on the morning of June 29th. By early afternoon, it had organized into a line racing eastward at nearly 60 miles per hour. By evening, it was crossing the Appalachians. Just after midnight, it moved offshore. In 12 hours, it traveled 700 miles. Winds along the path commonly exceeded 60 miles per hour. Numerous reports came in above 80 miles per hour. In Fort Wayne, Indiana, the peak gust reached 91 miles per hour, the highest wind gust ever recorded in that city in June or July. And the storm was moving toward the densely populated cities of the eastern seaboard, on one of the hottest days in the modern record. In Washington, D.C., the temperature on June 29, 2012, reached 104 degrees Fahrenheit. That was the hottest June temperature recorded in the capital in 142 years of continuous weather records. The derecho arrived that evening. 4.2 million customers lost power across the affected region: Indiana, Ohio, Kentucky, West Virginia, Pennsylvania, Virginia, Maryland, Delaware, New Jersey, and the District of Columbia. In Virginia alone, 1 million customers went dark, the largest non-hurricane power outage in the state's history. In Ohio, outages spread across roughly two-thirds of the state, producing the largest power outage in Ohio history. Ohio Governor John Kasich declared a state of emergency. Virginia Governor Bob McDonnell declared a state of emergency. The 911 emergency service was disrupted for more than 2 million customers across Virginia and West Virginia. In Northern Virginia, a key communications facility lost power, knocking out emergency services for a period of time in one of the most densely populated suburbs in the country. An Amazon Elastic Compute Cloud data center in Northern Virginia went down, taking Instagram, Pinterest, and Netflix offline for hours. That outage affected tens of millions of users across the country, a preview of how deeply digital infrastructure had become entangled with the physical grid. 22 people died, but that number understates the full mortality impact. The National Weather Service's official service assessment documented 34 additional heat-related deaths in the days and weeks following the storm. People who died not from the wind itself, but from the heat that arrived after the wind took out the air conditioning. That is the compound event in its most lethal form. The storm destroys the cooling infrastructure at precisely the moment the heat is most dangerous. The NWS service assessment contained a sentence that deserves to be read more widely than it has been. It stated, plainly and on the record, that unlike many major severe weather events in the recent past, this derecho was not forecast well in advance. It went further. Warm season derechos, in particular, are often difficult to forecast and frequently result from subtle small-scale forcing mechanisms that are difficult to resolve more than 12 to 24 hours in advance. 3 events. 3 separate occasions on which the forecast missed the threat until the storm was already accelerating. Iowa, 2020. Houston, 2024. Washington, 2012. That is not a coincidence. That is a pattern. And the physics behind it is the next part of this investigation. Because understanding why the warning consistently arrives after the damage has begun is the key to understanding everything that follows. There is a technical reason why derechos consistently arrive ahead of their warnings. It is not a failure of attention, or resources, or dedication. It is a structural mismatch between the speed at which these storms evolve and the speed at which the tools we have built to observe them can respond. Start with the radar. The National Weather Service operates 159 NEXRAD WSR 88D Doppler radar units across the United States, its territories, and cooperative installations in adjacent countries. The WSR 88D Weather Surveillance Radar 1988 Doppler is a mature and proven system. It can detect precipitation, estimate rainfall rates, and measure the radial velocity of targets moving toward or away from the radar dish. It is, by any reasonable assessment, a remarkable piece of infrastructure. It is also taking pictures roughly every 4 to 6 minutes. That is how long a full volume scan cycle takes. The complete sweep of the radar beam through its full range of elevation angles to build a 3-dimensional picture of what's in the atmosphere. 4 to 6 minutes. During that interval, a derecho traveling at 50 miles per hour covers between 3 and 5 miles. At 60 miles per hour, the speed of the 2012 event, it covers 5 to 6 miles per scan cycle. At the speed recorded on August 10th, 2020 over parts of Iowa, the leading edge of the storm was covering terrain faster than the radar could complete a full picture of what it was. The resulting image is always, by definition, of where the storm was, not where it is. The bow echo signature, the backward C shape that definitively indicates a derecho in progress, only becomes clearly visible on radar reflectivity and velocity products after the convective system has already organized and begun producing damaging winds at the surface. It is a confirmation, not a prediction. By the time a forecaster sees the signature and issues the warning, the storm is already there. The National Weather Service's average warning lead time for severe thunderstorm warnings is 10 to 15 minutes nationally. The National Severe Storms Laboratory, which operates under NOAA and has been working on next-generation warning technology for years, has documented this explicitly in its Grand Scientific Challenges Statement as a limitation requiring fundamental technological solutions. The NSSL's stated goal, through its Warn on Forecast program, is to extend severe thunderstorm warning lead times to 1 hour. As of 2025, that capability is still in demonstration phase, not operational deployment. 10 to 15 minutes. A derecho at 60 miles per hour covers 10 to 15 miles in that window. Imagine you're in Cedar Rapids, Iowa, on the morning of August 10th, 2020. You've seen the NWS had flagged marginal severe weather risk. You checked your phone at 8 a.m. and saw nothing alarming. You went to work. At 8:45 a.m., a severe thunderstorm warning was issued for your area. You had 8 minutes. The storm was already in Omaha. The second layer of the forecasting problem is the elevated mixed layer, the EML. This is the atmospheric mechanism that makes derecho days so deceptive on the morning of the event. The EML is a layer of dry, warm air that originates over the arid, elevated terrain of the southwestern United States and northern Mexico. As it spreads eastward over the moist, humid air of the Great Plains and Midwest, it acts as a cap, a kind of atmospheric lid that suppresses thunderstorm development during the morning hours, despite enormous amounts of energy building up below it. The result is a morning that looks benign or even pleasant. While thousands of joules per kilogram of convective available potential energy accumulate beneath an invisible ceiling. On the worst days, the CAPE values beneath the EML exceed 5,000 joules per kilogram. On June 29, 2012, the atmosphere across the corridor from Iowa to the mid-Atlantic registered CAPE values in excess of 5,000 joules per kilogram. The EML held the lid in place through the morning. Then the lid broke. When it does, the release is explosive and rapid. The thunderstorm complex that forms doesn't go through the gradual intensification cycle that gives forecasters time to adjust their outlooks. It erupts. The bow echo appears. The storm is already producing 100 miles per hour winds before the models have updated, before the watches have been issued, before most people in the path have any reason to think the afternoon is going to be dangerous. The Storm Prediction Center's risk categories, marginal, slight, enhanced, moderate, high, are probabilistic assessments of atmospheric conditions. They are honest descriptions of what the models can resolve at the time of issuance. On derecho days, the models frequently cannot resolve the convective trigger until the storm is already organizing. The SPC forecasters on the morning of August 10, 2020, were not wrong to issue a marginal risk. The atmosphere was not yet showing them what it was about to do. That is the forecasting gap, and it is structural. It cannot be fully resolved with more attention or more resources. It requires new tools, deployed operationally, that don't yet exist at scale, which means that for now, every derecho that forms does so with a window of surprise, a period during which the storm is accelerating and organizing while the warning system is catching up. And in that window, across hundreds of miles of grid infrastructure and millions of people's homes, the damage accumulates faster than any response can match. In the weeks and months after the May 16th, 2024 Houston derecho, a team of researchers from Florida International University and the University of Houston began doing something that sounds straightforward, but turned out to be deeply complicated. They tried to understand why the buildings failed. Not the utility poles, not the distribution lines, the skyscrapers. 18 of Houston's tallest downtown buildings were assessed after the storm. Between them, they had sustained more than 3,000 broken windows. The Wells Fargo Plaza, Enterprise Plaza, the Wedge International Tower, the Total Energies Tower, the Chevron Building Auditorium. Each of these structures was designed and engineered to withstand wind gusts up to 150 miles per hour. a specification set precisely to account for hurricane-force winds in a Gulf Coast city. The derecho produced 90 miles per hour gusts downtown. The buildings failed at 60% of their design wind load. Dr. Omar Metwally and his team at Florida International University began examining the physics of how a derecho wind behaves differently from a hurricane wind at equivalent speeds. They conducted experiments in a special wind chamber at FIU, altering the airflow to simulate the patterns of derechos versus hurricanes. Model buildings inside the chamber helped them evaluate the specific forces on the built environment. What they found complicates every structural engineering standard currently in use for tall buildings in the central and eastern United States. Hurricane winds are rotational. They approach from a consistent direction. Their speed varies, and their interaction with a building face produces forces that building codes have been refined to handle over decades of post-storm engineering surveys. Derecho winds are downburst winds. They descend rapidly from altitude and then rush outward horizontally at the surface, which means they arrive from unexpected angles, with sudden and extreme rates of change in both direction and speed. In the wind chamber, Metwally's team found that derecho-type downburst winds produce significantly stronger suction on the walls of urban buildings than hurricane winds at equivalent speeds. That suction, concentrated in ways that standard building codes do not model, is capable of dislodging the glass panels and curtain wall assemblies that modern skyscrapers use in place of traditional masonry. Hurricane Beryl struck Houston in July 2024, producing wind gusts comparable to those of the May derecho. Beryl caused dramatically less window damage. The two storms arrived at approximately the same speed. The buildings responded completely differently to each. Researcher Caliances at the University of Houston described something even more troubling in his team's analysis of the damage distribution. The pattern of broken windows wasn't uniform. Some facades showed significant damage at lower elevations, but less at higher elevations. A distribution that doesn't match what wind load models predict. Caliances and his team believe the wind tunnel effect, created between urban building clusters, may be amplifying the derecho downburst forces in ways that no existing building code or engineering standard accounts for. He stated plainly, "I think that is a big question here." The key question identified by the University of Houston team as of 2025 is this: can their simulations actually reproduce what happened in downtown Houston on May 16, 2024? The data they collected was observational, gathered in the aftermath, not during the event. The forces that dislodged 3,000 windows from buildings engineered for 150 miles per hour winds are not yet fully understood, not yet modeled with sufficient fidelity, and not yet incorporated into the codes that govern construction. 3,000 windows, 18 buildings designed for conditions twice as severe as what arrived. The gap between design assumption and physical reality is not an edge case. It is the central finding, and it is the same gap between what the infrastructure was built for and what the storm actually does that defines the entire derecho problem, from the grid in the ground to the glass 50 stories up. The storm doesn't respect the engineering, it operates by its own physics, and that physics, it turns out, is getting harder to model as the storms themselves change. And this is where the story takes a turn that most people haven't heard about yet, because the wooden utility pole, one of the most ordinary-looking objects in the American landscape, so familiar it disappears, is failing. Not metaphorically, not gradually in some distant theoretical future, physically, structurally, systematically, right now. Here is the baseline. As of 2023, according to analysis by the Smart Electric Power Alliance drawing on Department of Energy data, 70% of lines and transformers deployed on the U.S. grid are over 25 years old. 60% of circuit breakers are over 30 years old. 70% of transmission lines are over 25 years old. Most of the core infrastructure of the American electrical system was installed in the 1960s and 1970s at the peak of post-war suburban expansion, when the engineering assumptions embedded in the design reflected a climate and a demand profile that no longer exist. Large power transformers, the critical nodes that step voltage down and up across the transmission system, have a nominal design lifetime of approximately 40 years. As of 2014, the Department of Energy estimated the average age of large power transformers in the North American grid was 38 to 40 years. That estimate is now more than a decade old. The transformers have not gotten younger. The American Society of Civil Engineers, in its most recent infrastructure report card, assigned the U.S. energy infrastructure a grade of C-. That grade reflects not a catastrophic system, but a deteriorating one, a system whose deferred maintenance is accumulating faster than its renewal. And then there is the pole. Most utility poles in the United States are still made of wood. Wood has a nominal service lifespan of 25 to 50 years, depending on the species, the treatment, and the conditions in which it's embedded. After that range, the forces of weathering, moisture penetration, insect infestation, and ground-level rot begin to compromise the structural integrity that the pole needs to do its job, to hold wire under tension and wind. The poles that snap in a derecho are not all new poles, struck by an extraordinary force. Many of them are old poles pushed past their actual load-bearing capacity by winds that a newer, properly specified pole might have survived. The double pole phenomenon illustrates how deeply this has gotten out of hand. When a utility replaces an aging pole, the standard practice in many areas has been to install the new pole beside the old one and leave both in the ground, one energized, one decommissioned but still standing. Across the country, there are areas where this has happened repeatedly, leaving clusters of redundant poles of varying ages and conditions along the same right-of-way. When a derecho hits, these double pole configurations create unpredictable failure modes that complicate both the storm response and the restoration effort. In 2021, Hurricane Ida struck Louisiana. Energy lost more than 30,000 poles in that storm. Its main transmission tower carrying power into New Orleans, a hardened, engineered structure, collapsed in 150-mile-per-hour winds. Power to the Crescent City was cut for days. Critics noted at the time that Florida had spent billions hardening its distribution grid against exactly this kind of failure, replacing wooden poles with steel and concrete, undergrounding lines in the most flood and wind-prone areas. After comparable hurricane strikes, Florida restored power significantly faster than Louisiana. The difference wasn't the storms. It was the infrastructure those storms hit. The U.S. Energy Information Administration tracked average customer outage duration from 2013 to 2021. In 2013, the average U.S. electricity customer was without power roughly 3 to 4 hours per year. By 2021, that number had risen to approximately 7 hours per year, nearly double, with more than 5 of those 7 hours attributed to what the EIA classifies as major events, including severe weather. Power blackouts are estimated to cost the U.S. economy between $28 billion and $169 billion annually. Michael Weber, a professor of public affairs and engineering at the University of Texas at Austin, described the trajectory plainly. The accumulating wear on the components that hold the grid together, combined with weather that has been hotter and stormier in some regions, means that the wildfires and sustained blackouts we've already seen may be a preview of how an aging grid could falter spectacularly as weather becomes more extreme and demand for electricity continues to rise. That is not a prediction of catastrophe decades away. That is a description of a process already underway. 70% of the grid is over 25 years old. The distribution system, the last mile wires and poles that directly connect the high voltage transmission network to homes and businesses, accounts for approximately 70% of all power outages in the United States. It is the most exposed part of the system, the part with the least hardening, the least redundancy, and the most wooden poles. And it is the part that a derecho hits first, hardest, and across the widest possible front. The meteorological relationship between derechos and heat waves is not coincidental. It is causal. They share the same atmospheric engine, and understanding that engine is the key to understanding why the compound event is so much more dangerous than either phenomenon alone. The elevated mixed layer, the same mechanism that caps storm development in the morning and then releases it explosively in the afternoon, is a direct product of heat dome conditions. During a major summer heat wave over the central and eastern United States, a large stationary upper-level high-pressure area anchors itself over the south-central part of the country. The warm, dry air above the elevated terrain of the Rockies and Southwest flows eastward at mid-tropospheric levels, spreading over the humid Gulf air pooled across the plains and river valleys. The result is a cap, intense heat at the surface, dry, inhibiting air above it, and an enormous reservoir of convective energy building in between. That reservoir, when it releases, is what drives a progressive derecho. The Storm Prediction Center's own documentation on the subject is unambiguous. The meteorological conditions favorable for large-scale heat waves often are conducive to derechos. Specifically, and this geography matters, this is especially true from the upper Mississippi Valley and upper Great Lakes into the Ohio Valley and Northeast. That is Derecho Alley, the same corridor, the same cities. On June 29, 2012, multiple major U.S. cities set or tied all-time June temperature records on the same day the derecho swept through. Charlotte, North Carolina, reached 104 degrees Fahrenheit, a June record. Nashville, Tennessee, reached 109 degrees. Raleigh, North Carolina, hit 105 degrees. Washington, D.C. recorded 104 degrees, its hottest June temperature in 142 years of record-keeping. Then the derecho arrived, took out the power, took out the air conditioning, and left 4.2 million customers to sit in that heat. The NWS Service Assessment published in 2013 documented 34 additional deaths attributable to heat in the days and weeks after the storm. People who died not from the wind, but from what the wind left behind. A volunteer firefighter in Franklin County, Virginia, was killed by a falling tree while responding to an emergency call. 2 people in Big Island were killed in a storm-related house fire in the night. 2 children were killed by falling trees at a campground in New Jersey. The wind killed some people directly, but the compound event, heat without electricity, killed others more slowly in ways that don't make the initial news cycle and don't appear in derecho damage totals. In Houston, 12 years later, the same dynamic played out. The derecho struck on May 16th. The heat returned within days. Eric Berger, the meteorologist at Space City Weather, whose temperature forecasts are among the most accurate in the region, put it directly on Houston Matters Radio on May 21st. There will be no relief during the daytime, and even the nights are going to be really warm. Harris County reported deaths in the weeks following the storm that were attributed, at least in part, to the absence of cooling during a heat event. The assisted living center residents, hundreds of seniors without food, water, or air conditioning for days, represent the most visible manifestation of what happens when the cooling infrastructure collapses in summer. Mayor Whitmire's question about criminal neglect underscores how inadequate the human support systems are when power goes out for days rather than hours in a heat wave. The compound event doesn't just add the harm of 2 phenomena, it multiplies it. The storm destroys the infrastructure that mitigates the heat at exactly the moment the heat arrives. The populations most vulnerable to heat, the elderly, the very young, those without the mobility or resources to evacuate, are also the populations least equipped to survive extended outages without assistance. August 10, 2020, in Iowa added a 3rd layer. Drought. The agricultural damage was compounded by the fact that 31 Iowa counties were already in drought conditions. The flattened corn and soybean crops couldn't be dried down easily because of the soil conditions left by the drought. The compound event wasn't just derecho plus heat. It was derecho plus heat plus drought. 3 phenomena sharing the same atmospheric root. The SPC's documentation of this relationship concludes with a finding that should be at the center of every infrastructure resilience plan in the Midwest and Ohio Valley during a typical heat wave over the central and eastern United States. The meteorological conditions that produce the dome of heat above are the same conditions that produce the explosive convective release below. They are not coincidentally co-occurring. They are mechanistically linked. That means every major heat wave in this region carries embedded within it the atmospheric preconditions for a derecho. Not a guarantee, not a certainty, but a physical possibility baked into the same weather pattern for the duration of that heat dome's residence over the continent. And those heat domes, the atmospheric engine that drives all of this, are growing more frequent, more intense, and longer in duration. In November of 2023, a study was published in the journal Nature Climate Change that should have generated significantly more coverage than it received. Its author was Andreas F. Preen, a scientist at the National Center for Atmospheric Research in Boulder, Colorado. Its title was Thunderstorm Straight-Line Winds Intensify with Climate Change. Its findings were, by any reasonable measure, alarming. To conduct the research, Preen used a simulation called CONUS 404, a collaboration between NCAR scientists and the U.S. Geological Survey that models climate and hydrological conditions across the continental United States at a resolution of 4 kilometers per grid point across a period of more than 40 years. 4 kilometers across the entire continent, more than 40 years of simulated atmospheric history. Traditional weather station networks monitor straight-line winds from approximately 95 stations across the central United States. The CONUS 404 simulation gave Preen data from 109,387 points. That is roughly 1,150 times the density of the observational network. Enough resolution to capture the brief, localized wind events that weather stations routinely miss because they happen in the gaps between instruments. What the simulation showed was this: the geographic area of the central United States affected by damaging thunderstorm straight-line winds, the category that includes derechos, has increased 4.8 times over the past 40 years. Not 4.8%, 4.8 times. Preen then asked whether climate change was responsible for this increase, and he approached the question the way a physicist approaches it, from first principles through thermodynamics. Straight-line winds are generated when rain and hail at altitude evaporate, cooling the surrounding air, which then plunges downward and spreads outward at the surface with tremendous force. The speed of that downdraft depends on the temperature difference between the cool descending air and the warm ambient air surrounding it. A larger temperature difference produces a faster descent. A faster descent produces a stronger surface wind. Climate change, by warming the ambient air more rapidly than it warms the upper atmosphere, increases that temperature differential. It makes the descent faster. It makes the surface wind stronger. The physics is not controversial. It follows directly from basic atmospheric thermodynamics. The question was, how much? The theoretical prediction, the rate at which straight-line wind intensity should increase per degree Celsius of warming, is approximately 7.5% per degree. What Preen found in the CONUS 404 data was that the actual observed rate was approximately 13% per degree Celsius, nearly double the theoretical prediction. The storms are intensifying faster than the physics textbook said they should. Preen made the implication explicit in the NCAR press release accompanying the study's publication. You have a 5 times higher chance of getting hit by a damaging straight-line windstorm during summer in the central U.S. nowadays compared to the 1980s. 5 times. In 4 decades, while the grid that will absorb that damage has aged without proportional investment in hardening. The same month Preen's study was published, a separate team of researchers published a companion finding in the Bulletin of the American Meteorological Society. This team had taken a different approach. Rather than modeling trend lines, they took the August 10, 2020 Midwest derecho, the costliest event on record, and resimulated it under end-of-century warming conditions. They ran the simulation twice, under an intermediate emission scenario and under a high emission scenario. Their conclusion: a future derecho equivalent to August 10th, 2020 could impact a geographic area 50 to 100% larger than the original event. 50 to 100% larger. The August 10th storm already covered 770 miles and affected 8 states. A storm 50% larger on the same track would extend well into the eastern seaboard. A storm 100% larger in geographic footprint, a scenario the physics does not rule out, would encompass a swath of the country too large to usefully describe in terms of individual states. In 2024, a team led by Walker Ashley at Northern Illinois University published the most comprehensive forward projection of U.S. derecho frequency and intensity yet produced. Their study, accepted for publication in the Journal of Climate in October 2024, used high-resolution, convection permitting dynamically downscaled regional climate simulation output, the most computationally sophisticated method available for this question. They examined three 15-year epochs, a historical period from 1990 to 2005, and two late 21st century periods employing both intermediate and pessimistic greenhouse gas scenarios. The result was consistent across both future scenarios. Mesoscale convective system-based windstorms, including derechos, are projected to be more frequent, more widespread, and more intense. Not under the pessimistic scenario only, under both. Prain's own closing statement in the NCAR press release serves as an honest summary of where the science stands. It is crucial to incorporate the increasing risk of straight-line winds when planning for the impacts of climate change so we can ensure the future resiliency of infrastructure to this frequently neglected peril. Frequently neglected. Those two words are doing a lot of work. The Storm Prediction Center's climatological map of moderate to high intensity derecho occurrence in the United States, compiled from 22 years of severe weather data by researcher Dennis Kane, is one of the most instructive documents in American infrastructure risk assessment. It is also one of the least consulted by the people responsible for maintaining the infrastructure it describes. The map shows two primary axes of derecho activity. The warm season axis runs from the upper Mississippi Valley, Minnesota, Iowa, the Dakotas, southeast into the Ohio Valley, passing through Wisconsin, Illinois, Indiana, and Ohio before continuing into Pennsylvania and the Mid-Atlantic. This is the corridor where the most historically destructive events have concentrated. It is the corridor of August 10th, 2020 and June 29th, 2012. The second axis runs from the Southern Plains, Oklahoma, Kansas, Missouri, northeast into the mid-Mississippi Valley. It intersects the first axis across a broad region centered roughly on the Iowa-Illinois-Missouri triangle. The overlap of these two axes, the densest region of derecho activity on the continent, is what the SPC calls Derecho Alley. It encompasses some of the highest density inland population centers in the United States: Chicago, the third largest city in the country, St. Louis, Indianapolis, Columbus, Cincinnati, Louisville, Kansas City, Memphis, Nashville, Minneapolis. None of these cities sit on a coastline. None of them have experienced the sustained political and regulatory pressure to harden distribution infrastructure that coastal cities have faced after repeated hurricane seasons. Most of their grid infrastructure was built in the same post-war decades as the rest of the country's, the 1960s and 70s, and has been maintained but not fundamentally redesigned in the half-century since. The Derecho Alley corridor also directly overlaps with the region the SPC identifies as most susceptible to the compound event, the northern fringe of quasi-stationary summer heat domes, where the elevated mixed layer creates the pressure lid that concentrates energy before explosive release. Chicago is in this zone. Columbus is in this zone. The same atmospheric pattern that produces a brutal Midwest heat wave is the pattern that breeds progressive derechos on its northern edge. During just the first half of 2023 alone, the Storm Prediction Center recorded more than 7,000 reports of severe caliber thunderstorm winds across the United States. That number spans all straight-line wind events, not only derechos, but it describes the background frequency of damaging convective wind in a country that has broadly failed to treat this as the systemic infrastructure threat it is. The July 15, 2024 derecho, one of at least two significant derecho events in that calendar year, swept from eastern Iowa through much of Illinois and into Indiana. A weather station at the Henry Marina in Henry County, Illinois, recorded a measured wind gust of 80 miles per hour. 3 miles south of Camp Grove in Marshall County, Illinois, a measured gust of 105 miles per hour was recorded, fast enough to destroy structures not designed for hurricane loading. The Storm Prediction Center formally classified the July 15th event as a derecho based on its damage swath exceeding 400 miles. Derecho season in the United States runs roughly from May through August, with more than 75% of events concentrated in those months. That is also, not coincidentally, the heart of the summer heatwave season. It is cooling season. It is the period when the grid is under peak load from air conditioning demand, when the infrastructure is already stressed before the storm arrives, and when the ambient temperatures after a power loss are most immediately dangerous to human life. The exposure map, in other words, is not a map of where derechos might eventually become a problem. It is a map of where they already are a problem, occurring on a roughly annual cycle in the most population-dense interior regions of the country, against infrastructure that was not designed with them in mind. Here is the institutional gap at the center of this story. Coastal utilities, particularly in Florida, and increasingly in parts of Louisiana, following the devastating lessons of Hurricane Ida in 2021, have spent billions of dollars over the past 2 decades hardening their distribution grids against high wind events. They have replaced wooden poles with steel and concrete structures. They have buried distribution lines underground in the most flood and wind vulnerable corridors. They have reinforced substations, upgraded transmission towers, and redesigned vegetation management programs to reduce the number of trees capable of falling on energized lines. The motivation has been explicit and documented. Repeated hurricane strikes, each one producing weeks-long outages and billions in restoration costs, have created sustained political and regulatory pressure on coastal utilities to invest in physical hardening. Florida, after multiple catastrophic hurricane seasons, made this investment. When comparable storms subsequently struck the state, Florida restored power faster than neighboring states had after equivalent events. After Hurricane Ida destroyed more than 30,000 utility poles across Louisiana in 2021, critics were direct. Florida had done the work. Louisiana had not. The difference in restoration time was visible and measurable. Inland utilities have largely not made the same investment. The primary design reference hazard for most Midwestern and Ohio Valley distribution infrastructure has been the tornado, a highly localized, intensely powerful, but geographically narrow event. A tornado might affect a single distribution circuit. A strong EF3 or EF4 tornado might take out a corridor a few hundred yards wide over a path of several miles. A derecho takes out everything across a 50 to 100 mile wide corridor, stretching hundreds of miles. The mutual aid system, the arrangement by which utilities in unaffected areas send crews and equipment to help restore power after major events, was designed with single event disasters in mind. When one utility is hit by a tornado or an ice storm, neighboring utilities dispatch crews. The neighboring utilities' systems are intact. Their crews are available. The logistical challenge is getting the people and equipment to the damage. A derecho that spans 5 states simultaneously leaves no unaffected neighbors nearby. The mutual aid system activates, as CenterPoint Energy demonstrated in May 2024, mobilizing resources from 8 states, but the travel time, the coordination overhead, and the sheer geographic scale of the simultaneous damage means the system is always catching up, always working at the edge of its capacity. The Department of Energy's review of power outage restoration following the June 29, 2012 derecho documented this explicitly. The 2-day restoration rate after that event was 45%, compared to 55% or higher after other comparable storms. Not because utilities weren't trying, because the geographic scope of the damage was too large for the mutual aid system to absorb at the pace that prior experience had established. Iowa 2020 confirmed it. The IDHSEM post-event review found that there was not a backup process for communication and coordination for long-term power and cellular outages. Emergency managers testified that semi-trucks of ice arrived unprompted in communities that didn't need them, while communities that did needed them waited. The system was overwhelmed not by the complexity of a single location's damage, but by the simultaneous nature of damage across hundreds of locations. Michael Jewell, a longtime regulatory attorney who has worked on Texas power grid issues, put the fundamental distinction plainly in the aftermath of Hurricane Beryl's 2024 landfall. The hurricane is throwing trees around, taking out wires. It's not that there wasn't enough power. The generation side of the grid, the plants that produce electricity, largely survived both the Houston derecho and subsequent events. What failed was the delivery side, the poles, the wires, the last mile infrastructure. CenterPoint Energy, under pressure from the Public Utility Commission of Texas, following both the May 2024 derecho and Hurricane Beryl in July 2024 committed to a multi-year infrastructure hardening program, accelerated vegetation management, replacement of wooden poles with steel and concrete in high-risk areas, undergrounding of select distribution lines. The program was described in filings as taking years to implement, years. While derecho season arrives each May, the pattern in this data is clear. Coastal infrastructure has been hardened by decades of hurricane experience, regulatory pressure, and public accountability after catastrophic outages. Inland infrastructure sits in the highest frequency derecho corridor in the world, on aging poles and wires designed for the weather of the 1960s, with restoration systems calibrated for localized events that a derecho, by definition, is not. The definition of a derecho was revised in January 2022, then again in May 2025. NOAA and Environment and Climate Change Canada moved to an algorithmic, objective standard specifically because the prior definitions were ambiguous and the events being documented no longer fit cleanly within them. When the regulatory body revises the definition twice in 3 years, the thing being defined has changed. Every time a story like this one reaches a significant audience, every time an event on the scale of Iowa 2020 or Houston 2224 lands in the national conversation, a different kind of explanation begins circulating. And before this investigation reaches its assessment, it's worth addressing that explanation directly, because it deserves an honest answer grounded in physics rather than dismissal. The most common alternative explanation for events like the August 10th, 2020 derecho involves HAARP, the High Frequency Active Auroral Research Program, a government-funded research facility in Alaska that operates high-frequency radio transmitters to study the ionosphere. In some corners of the internet, HAARP is described as a weather modification system capable of steering or intensifying storms. Related claims involve chemtrails, directed energy systems, or some combination of government technology and deliberate concealment of the real cause of extreme weather events. I want to address this directly, not because the claim is dangerous, but because the impulse behind it is understandable, and because replacing a wrong explanation with the correct one is important. HAARP's maximum transmitted power output is 3.6 megawatts. The August 10th, 2020 Midwest derecho released energy equivalent to multiple petajoules. 1 petajoule is 1 quadrillion joules, or approximately 10 to the 15th power joules. The ratio of HAARP's output to the energy released by that storm is roughly equivalent to attempting to heat an ocean with a birthday candle. The energy budget makes the claim physically impossible by many orders of magnitude, not implausible, impossible. More fundamentally, derechos were formally documented in scientific literature in 1888 by Dr. Gustavus Hinrichs at the University of Iowa, decades before any of the technologies invoked in modern weather manipulation claims existed. The Bow-Echo mechanism, the self-sustaining, cold pool-driven convective engine that produces these storms, is fully described by atmospheric thermodynamics that have been understood since the 1950s and 1960s. The physics requires no external forcing. The storm builds itself, sustains itself, and accelerates itself through mechanisms that have been replicated in laboratory simulations, verified against observed events, and published in peer-reviewed literature for more than half a century. The conspiracy explanation is wrong. But here is what is true. There is a real gap between what institutions knew and what they communicated. Steve Okonek, Lynn County Emergency Management Director, told Iowa Public Radio he had never heard of a derecho before one destroyed 98% of his county's power infrastructure. The IDHSEM review documented that multiple interviewees across the emergency management system were unaware of the severity of the incoming storm. The NWS's own service assessment of the 2012 event stated the storm was not forecast well in advance. The gap between institutional knowledge and public communication is real. The failure was not concealment. It was ignorance, and in some cases, the absence of adequate systems for translating what forecasters did know into actionable warning for the populations in the path. That distinction matters. A conspiracy of concealment has a villain and a solution. Expose the villain, and the problem is solved. An institutional failure of knowledge, planning, and communication has no villain, but it has a much clearer path to improvement. Better warning systems, better public education about derecho risk, better infrastructure hardening in the exposed corridors, better mutual aid capacity sized for multi-state simultaneous damage. The real human fingerprint on derechos, the actual place where human decisions are making these events more damaging, is not in some secret program. It is in the Preen finding. 13% intensification per degree Celsius, documented in a 40-year simulation at 4-kilometer resolution, published in Nature Climate Change. It is in the 70% of the grid that is over 25 years old. It is in the building codes that don't account for downburst suction forces. It is in the emergency management frameworks sized for tornadoes, not for storms that cover half a continent simultaneously. The real story doesn't need the conspiracy. The ordinary physics is alarming enough. Part 14. 3 interpretations. What the evidence means. Any honest investigation has to do something that is genuinely uncomfortable, present the most charitable interpretation of the evidence alongside the most alarming one, and resist the temptation to dismiss the first just because the second feels more urgent. So let's do that. Interpretation. 1. The most generous reading of the data goes like this. Derechos are a known, well-documented, recurring phenomenon. The United States has been experiencing them since long before any of the research cited in this investigation was published. The August 10, 2020 event was severe and costly, but the $11 billion price tag reflects decades of deferred maintenance on agricultural infrastructure, an aging grid that would have been vulnerable to any major convective event, and the simple fact that the storm hit an unusually favorable track over unusually high-value agricultural land. The 2012 event hit the eastern seaboard during an unusual heat wave that amplified its human cost well beyond what the storm alone would have produced. Under this interpretation, the NOAA definition revisions of 2022 and 2025 reflect scientific improvement, better tools, better algorithms, more consistent application of existing criteria rather than evidence of changing events. The Preen finding of a 4.8 times expansion in geographic footprint is real, but it describes the output of a high-resolution climate model, not a direct observation, and model outputs carry inherent uncertainty ranges. The institutional failures documented in Iowa, the emergency manager who didn't know derechos existed, the absence of backup communication protocols, reflect a planning gap that can be closed through better public education and improved emergency management frameworks without requiring fundamental infrastructure redesign. Under this interpretation, the most appropriate response is targeted: harden the grid in the highest exposure corridors, improve mutual aid capacity, update building codes to account for downburst physics, and invest in the Warn-On Forecast program to close the lead time gap. These are meaningful, achievable improvements. Interpretation? 2. The intermediate position accepts the climate signal as real, but emphasizes that its full operational impact remains decades away and that the most urgent action is infrastructure investment rather than alarm. The Preen finding is robust. The Ashley et al. 2024 projections showing increased frequency under both emission scenarios are compelling, but the research on future derecho behavior also shows genuine complexity. A 2023 study in the Journal of Geophysical Research found that the June 2012 derecho could actually shrink in the first half of its life cycle under future warming conditions due to the role of relative humidity and convective inhibition changes. The science does not uniformly project stronger events. It projects more variable events with extremes shifting upward. Under this interpretation, the most urgent intervention is grid hardening. If the distribution infrastructure in Derecho Alley were brought to the hardening standards that Florida has applied to its hurricane-exposed grid, steel and concrete poles in high-risk areas, underground lines in the most vulnerable corridors, reinforced substations, The damage from derecho events at current frequency and intensity would be dramatically reduced. This is a trillion-dollar infrastructure problem, not primarily a meteorological one. Interpretation. 3. The most concerning reading begins with a compound observation that deserves direct attention. The derecho definition was revised in January 2022. It was revised again in May 2025. Both revisions moved in the same direction, expanding and tightening the criteria to capture events as they actually occur rather than as prior research expected them to occur. When an official scientific definition is revised twice in 3 years to better fit observed reality, it is legitimate to ask whether the events have changed, not just the documentation. The Prien finding of 13% intensification per degree Celsius is not a model artifact. It represents a real-world observation confirmed against the CONUS 404 simulation, verified against specific events including August 10, 2020. The fact that the observed rate exceeds the theoretical prediction is a signal that should prompt scrutiny, not comfort. When a measured phenomenon is intensifying faster than the physics textbooks predicted, the appropriate response is not to assume the discrepancy will resolve itself. Meanwhile, the grid is being asked to do more. Power demand in Texas, according to grid operators quoted in 2024 reporting, could nearly double within 6 years, driven by AI data center construction, electric vehicle charging infrastructure, and population growth in precisely the same southern and midwestern regions most exposed to derecho risk. The margins available to absorb shock events are shrinking at the same moment the shock events are growing. Under this interpretation, the compound of increasing event intensity, expanding geographic footprint, aging infrastructure, and rising baseline demand describes a trajectory that is not correctable by incremental hardening alone. It describes a systemic mismatch between the energy infrastructure the United States has inherited and the meteorological reality it is now operating in. The data that would distinguish between these three interpretations does not yet fully exist. The NWS has not yet released a climatological frequency analysis using the new May 2025 algorithmic definition applied retroactively to the historical record. That analysis, when it exists, will reveal whether the pattern of recent events represents genuine intensification or improved documentation of a stable underlying frequency. It is the single most important piece of data this investigation is waiting for. Until then, the evidence supports all three interpretations to varying degrees. What it does not support is inaction, under any reading. Strip this investigation to what the evidence actually confirms, and here is what you are left with. The August 10th, 2020 Midwest derecho produced wind speeds estimated at 140 miles per hour over Cedar Rapids, Iowa, traveled 770 miles through 8 states in 14 hours, and at $11 billion became the most expensive single thunderstorm event in modern U.S. history. 1.9 million customers were affected by power outages. The Lynn County Emergency Management Director told Iowa Public Radio he had never heard of the type of storm that had just destroyed 98% of his county's electrical infrastructure. The June 29, 2012, North American derecho took down power for 4.2 million customers across a dozen states and the District of Columbia, killed 22 people directly, produced 34 additional heat-related deaths in the weeks afterward, disrupted 911 service for more than 2 million customers in Virginia and West Virginia, and arrived on the same day Washington, D.C. recorded its hottest June temperature in 142 years of continuous records. The National Weather Service's official assessment stated explicitly that the event was not forecast well in advance. The May 16, 2024, Houston derecho struck the energy capital of the world with estimated winds of 100 miles per hour, left 1 million customers without power, killed 8 people, forced CenterPoint Energy to replace more than 400 miles of primary electrical wire and approximately 1,600 poles and 1,600 transformers, and generated an emergency response cost filing of approximately $450 million. Buildings designed to withstand 150 miles per hour winds sustained glass damage that buildings in Hurricane Barrel, at comparable wind speeds, Did not. Those are the confirmed facts. They do not require a model projection or a climate scenario. They are what already happened. On top of that confirmed foundation, the research adds the following. The geographic area affected by damaging straight-line winds in the central United States has expanded 4.8 times in 40 years, according to a simulation that examined 109,387 data points at 4-kilometer resolution, published in Nature Climate Change in November 2023 by NCAR scientist Andreas Prine. The observed intensification rate is 13% per degree Celsius, significantly exceeding the theoretical prediction of 7.5%. Under end-of-century warming scenarios, a derecho equivalent to August 10th, 2020 could impact a geographic footprint 50 to 100% larger. 70% of the U.S. power grid's lines and transformers are over 25 years old. Most utility poles are still made of wood. The American Society of Civil Engineers graded U.S. energy infrastructure C-. Average customer outage duration has nearly doubled since 2013, with severe weather accounting for most of the increase. The genuine uncertainties are real and should be named honestly. The research on how climate change affects future derecho behavior does not point uniformly in one direction. Some studies project stronger events under warming. Others project that changes in relative humidity and convective inhibition could cause some events to decay earlier. The science on frequency is more consistent. Multiple independent studies project increases in frequency and geographic extent. But the magnitude and regional distribution of those increases carry genuine uncertainty ranges. The University of Houston's research team working on the downtown Houston building damage reached a conclusion that stands as an honest summary of where this specific question sits. Can we reproduce what happened on our computers? The answer, as of 2025, is not yet. The wind tunnel dynamics in urban canyons, the specific suction forces that dislodge 3,000 windows from buildings rated for 150 miles per hour, are not yet fully understood. And the National Weather Service's lead time for severe thunderstorm warnings remains 10 to 15 minutes nationally, against a storm type that can cover that distance in the same interval. These open questions are not arguments for inaction. They are arguments for the kind of sustained, evidence-based attention that serious infrastructure risk demands. The Warn on Forecast program exists because the forecasting gap is real and documented, and the technology to close it is within reach. The grid hardening that Florida has demonstrated is achievable in the Midwest. The building code updates that the FIU and University of Houston teams are laying the scientific foundation for can be written. What is missing is not the science. The science, as this investigation has documented, is ahead of the institutions responsible for acting on it. What is missing is the urgency, the treatment of derecho risk as the systemic, compounding infrastructure scale threat that the evidence describes. The primary question this investigation opened with, why does a storm this powerful consistently arrive ahead of its warning, and what does that mean for the infrastructure it destroys, has an answer. The storm outruns its warning because it is self-generating and self-accelerating, driven by a thermodynamic engine that only becomes identifiable on radar after it is already organized. And because the average warning lead time of 10 to 15 minutes was calibrated for a different era of technology and a different threat profile than the one this country now faces. What it means for the infrastructure: $11 billion, 4.2 million customers, 1 million customers in the energy capital of the world. Buildings built for 150 miles per hour, destroyed at 60% of their design load, and a definition that was revised in May of 2025, algorithmically, formally, officially, to better capture events as they actually occur. When the definition changes, the storm has changed. The Iowa Department of Homeland Security and Emergency Management's post-event review of the August 10th, 2020 derecho contains a sentence in its findings section that has stayed with this investigation from the beginning. There was not a backup process for communication and coordination for long-term power and cellular outages. That sentence is not a criticism of the emergency managers who wrote it. It is an honest acknowledgement of the gap between the systems that existed and the storm that arrived. And it is still true, not just in Iowa, but in most of the jurisdictions along the Derecho Alley corridor, where emergency planning frameworks have been developed for tornadoes, for ice storms, for individual events with defined footprints and predictable restoration timelines. The derecho is none of those things. It is a multi-state, simultaneous infrastructure failure event, arriving with 10 to 15 minutes of warning on average during the hottest part of summer against a grid that was built 50 years ago on wooden poles. Andreas Prehn, the NCAR scientist whose research produced the most specific and documented climate signal in this investigation, closed his work with a statement that deserves to be read as both a scientific conclusion and a policy directive. It is crucial to incorporate the increasing risk of straight-line winds when planning for the impacts of climate change, so we can ensure the future resiliency of infrastructure to this frequently neglected peril. Frequently neglected. The storms are not neglected by meteorologists. The SPC watches for bow echoes every day during derecho season. The NWS issues warnings as fast as the technology allows. The research community, Prehn, Ashley, Metwally, Kaliansis, and dozens of others, is doing exactly the work that needs to be done. The neglect is in the gap between what the research shows and what the institutions responsible for infrastructure have done with it. Closing that gap is not a meteorological problem. It is a planning problem, a political problem, a budget problem, and, in the most straightforward sense, an awareness problem. Because awareness is where it begins. Because you cannot prepare for a threat you have not been told is real. That is what this channel is for. Signal Watch will be watching every time a severe thunderstorm watch goes up in the Ohio Valley or the lower Mississippi Valley. We will be watching the SPC's implementation of its May 2025 algorithmic definition and the frequency data that emerges from it. We will be watching for the next major event, and we will be here when it arrives, not to announce that we predicted it, but to give you the clearest, most evidence-grounded account of what it was and what it means. The storm doesn't wait for awareness to catch up. Neither should we.